Today we are going to go over 5.4 complex numbers. All right, so this is a Algebra 2 topic. I know the last topic, 5.3, was quadratic formula, and you would have done that in Algebra 1. So, motivating the lesson. You have explored several ways to solve quadratic equations. You can find the x-intercepts on a graph. You can solve by completing the square, or you can use quadratic formula. What happens, though, if you try to use quadratic formula on an equation whose graph has no x-intercepts? So let's take a look together. The graph of y equals x squared plus 4x plus 5 at the right shows that this function has no x-intercepts. It never crosses the x-axis. So watch what we're going to do. We're going to use quadratic formula. So quadratic formula is x equals negative b plus or minus square root b squared minus 4ac all over 2a. So b, what is b? b is 4. So that's negative 4 plus or minus square root, 4 squared minus 4. What's a? A is 1. And what is c? C is 5. So this is negative 4 plus or minus square root 16 minus 20 over 2. And we get a negative under the square root. All right, so this is a problem. So throughout the development, so we can't finish it right now. We don't have enough tools in our math tool belts to figure it out. So throughout the development of mathematics, new sets of numbers have been defined in order to solve problems. Mathematicians defined fractions and not just whole numbers. Then they did negative numbers and not just positive numbers. They did irrational numbers and not just rational, like square root 3. For the same reasons, we also have square roots of negative numbers, not just square roots of positive numbers. Numbers that include the real numbers as well as the square roots of negative numbers are called complex numbers. So here's a little history connection. Since the 1500s, the square root of a negative number has been called an imaginary number. In the late 1700s, the Swiss mathematician Leonhard Euler, I know it looks like Euler, but it's pronounced Euler, introduced the symbol I to represent the square root of negative 1. Again, he used I to represent the square root of negative 1. He wrote, "It is evident that we cannot rank the square root of a negative number amongst possible numbers, and we must therefore say that it is an impossible quantity. But notwithstanding this, these numbers represent themselves to the mind. They exist in our imagination, and we still have a sufficient idea of them. Since we know that by square root negative 4 is meant a number which multiplied by itself produces negative 4, for this reason also nothing prevents us from making use of these imaginary numbers and employing them in calculation. Defining imaginary numbers made it possible to solve previously unsolvable problems." So, to express the square root of a negative number, we use an imaginary unit called I. So here's what I want us to do here. So if I had the square root of that negative 4, I could say that's the square root of 4 times the square root of negative 1. Well, what is the square root of 4? It's 2. And now we have newly defined I is the square root of negative 1. So this is 2 times I, or 2I. Let's do one more, just to make sure you're getting the hang of it. What if I said I had the square root of negative 36? We would say that's the square root of 36 times the square root of negative 1. What's the square root of 36? It's 6. What is the square root of negative 1? It's I, so that's 6i. All right, so let's define a complex number. A complex number is a number of the form a plus bi. So if you look here, right now, we only had the real numbers. We only had the real numbers, and you knew they could be fractions or not written as a fraction. And if it was a fraction, it could be an integer or a natural number. Now we're going to open this up. It's really, really quite exciting. Okay, so let's do the back here, example 1. If I want to simplify the square root of negative 9, watch what we're going to do. You're going to make this the square root of 9 times the square root of negative 1. Well, what is the square root of 9? It's 3. Well, what is the square root of negative 1? It's I. So that's 3i. All right, letter B. We're going to make this the square root of 12 times the square root of negative 1. All right, unfortunately, the square root of 12 is not a perfect square like 9 or 16 or 25 or 36. But what we can do is we can do what's called a factor tree. This is 2 times 6. 6 is 2 times 3. Then you have a pair of 2's. So that's 2 square root 3. And then the square root of negative 1 is I. Now, we put an I in front of a radical just so it doesn't look like it's underneath. All right, let's try letter C. We're going to make this the square root of 64 times the square root of negative 1. Okay, what's the square root of 64? It's 8. And what is the square root of negative 1? It's I. All right, so now let's see it in action. Okay, this will be fun. If I want to solve for x squared, I can subtract 3 from both sides. And then remember, you actually have to do the plus or minus square root to both sides. We actually never, ever leave a negative under the square root. So what you're going to do is you're going to rewrite this as the square root of 3 times the square root of negative 1. So then this will be plus or minus. Now, the square root of negative 1 is I, and the square root of 3 doesn't cancel. But don't forget the plus or minus, okay? Don't forget this plus or minus symbol. All right, complex numbers have many applications, particularly in science and engineering. To measure the strength of an electromagnetic field, a real number represents the amount of electricity, and an imaginary number represents the amount of magnetism. The state of a component in an electronic circuit is also measured by a complex number, where the voltage is a real number and the current is an imaginary number. So let me pause there a moment. So I know oftentimes as a math teacher, I hear students say, math is stupid. When am I ever going to use this? Well, electrical engineers use this. Some scientists use imaginary numbers. So even if you aren't going to go into that field, at least have an appreciation for the people who are doing it, because I think we enjoy having cell phones, which require electricity. I think we like lights in our home and air conditioning, microwaves, ovens, refrigerators. There are a lot of things that we enjoy that take electricity. So even though some of us are not going to go into that field, we need to be appreciative of those people who learn it and know how to use it, because we are benefiting from that. All right, the properties of calculations with complex numbers apply to these types of physical states more accurately than calculations with real numbers. In the investigation, you'll explore patterns in arithmetic with complex numbers. So the good news is this is super simple. If you have addition, all you do is you add the real parts. Please write this down. And you add the imaginary parts. Again, please write this down. You add the real parts and you add the imaginary parts. It's super simple. So 2 plus 3 is 5. Negative 4i plus 5i is plus 1i. And it's okay to do 5 plus I. Now, there is always a method to my madness. You notice that I kept doing f of x minus g of x, f of x minus g of x. What do you have to be careful with when you do f of x minus g of x? Well, you have to distribute the minus sign, okay? You have to distribute the minus sign. So we're going to do that here as well. So I've been working for your benefit. I have been working to set you up for success. Now, you have to distribute that minus sign, then you can combine real parts and imaginary parts. So I take my 2 minus 3, again, 2 minus 3, what's that? 2 minus 3 is negative 1. Now let's do the imaginary parts. What's minus 4i minus 5i? Again, you have a minus 4i minus 5i. That's minus 9i. All right, letter C. On this one, you're going to FOIL. Okay, FOIL. You're going to do the first. 2 times 3 is 6. The outer is a positive 10i. The inner is a minus 12i. And the last is minus 20i squared. One more time, I FOILed. I did the first, the outer, the inner, the last. Now I need to go back because I realized I didn't emphasize this back here, so let me go back and do a better job. Here it is. I squared equals negative 1. I is the square root of negative 1, but I squared is negative 1. So let me come back here now. I'm going to combine my like terms, and I'd get 6 minus 2i, but I squared is negative 1. Okay, that's part of the definition of an imaginary number, is I. Okay, I is the square root of negative 1, and I squared is negative 1. So I get 6 minus 2i plus 20. So that's 26 minus 2i. All right, that finishes the notes.